Greetings and welcome to the Astronomy Picture of the Day podcast. Today's picture is titled RCW 86, Historical Supernova Remnant. So what do we see here? Well, here we see an image showing the sky, and those little wisps of gas that we see there in the brighter red are actually part of a supernova remnant. Now, this remnant was seen to have exploded nearly 2,000 years ago, back in the year 185. And it was actually recorded by Chinese astronomers who recorded the presence of a new star at this location in the sky. Now, since then, over those nearly 2,000 years, the material has expanded outward. So this is 2,000 years worth of expansion. But if you can imagine measuring that material, figuring out how fast it's moving, you could trace it back and find out that it did occur back that long ago. That a new star would have been in the sky, and this is the material that has been expanding outward since that time. Now, supernovae come in two types. There are type 1 and type 2. A type 2 is a massive star at the end of its life which explodes. As it gets to the end of its life, it uses up all the different types of fuel, builds up a core of iron, and becomes completely unstable and explodes. This was a type 1 supernova. Now, type 1 is different in that it was not a massive star that exploded, but the remnant of a dead star known as a white dwarf. Now, our sun will eventually become a white dwarf, and there's a limit to their stability. They can only become so massive before they collapse inward. For a white dwarf star, it's a mass of about 1.4 times the mass of our sun. So most stars will become a white dwarf that is much less massive than that, and it can never become a supernova. However, in cases where it's right at that limit, then you can have that explosion. Essentially, there's ways for stars to transfer mass from one to another. So if a white dwarf near an ordinary star and it pulls some mass from that, it can push it over that limit. You can think of it as an old table, maybe a little rickety, and you start stacking books on it. It'll hold quite a few of those books, but eventually you will put one too many book on it and the table will collapse. That's what happens to the star. The star will do the very same thing. You can put so much mass on it, transfer just so much, but once you break that limit, the entire star undergoes fusion at once and the whole thing explodes, leaving nothing behind. So all that's left here is the material expanding outward. There is nothing left at the core, which is different than what happens with a type 2 supernova. In that case, you could have a neutron star or a black hole left behind after the explosion. Here, there is nothing. These supernovae are very important because they are all the same. Every single one occurs from the same type of object that has exactly the same mass. So they should all then theoretically reach the same brightness. That allows us to use them to determine distances. Not so much within our own galaxy because we don't see lots of supernovae in our galaxy, but we see thousands each year in other galaxies, and we can use those as distance determinations or standard candles, way to be able to measure distances to those galaxies once a supernova like this goes off in them. So that was our picture of the day, titled RCW 86, Historical Supernova Remnant. We'll be back again tomorrow for the next picture, previewed to be Tranquility and Serenity. So we'll see what that is about tomorrow. And until then, have a great day, everyone, and I will see you in class.